The task that the biological brain has to solve is very, very different than what an artificial network has to do. And to me, the clearest example of this distinction is whatever solution the brain has learned to produce intelligent behavior has to go through this sort of genetic bottleneck where we cannot pass on fully formed brains, right? So instead what we do is we compress whatever algorithm we have, whatever model we have into DNA, which is, a couple gigabytes, and then we pass it off to our offspring and they have to rebuild this. So whatever solution that favors is going to be good for passing through this bottleneck, and that's fine. But there's no reason why artificial intelligence has to pass through a similar bottleneck. So the solutions are going to look very different.
Hey there, I'm your host, Kan Jun, and we are an independent research lab developing AI agents that mirror the fundamentals of human-like intelligence and that can learn to safely solve problems in the real world. On our podcast, we interview researchers about their behind-the-scenes ideas, opinions, and intuitions that are hard to share in papers and talks. We hope you learn as much as we have in our quest to understand and build the mind.
Rylan Schaeffer is a PhD student at Stanford studying the engineering, science, and mathematics of intelligence. He authored the paper, Are Emergent Abilities of Large Language Models a Mirage?, as well as other interesting refutations in the field that we'll talk about today. He previously interned at Meta on the Llama team and also at Google DeepMind.
Thank you, Rylan. Welcome to the podcast. We're super excited to have you today.
Cool. Thanks for inviting me. I'm super excited to be here.
Your research interests have been very diverse. Tell us the story of how you developed your initial research interests and then how they've evolved over time.
Absolutely. So I guess it depends on how long you want the answer to be. The short answer, I can go into different levels.
The long answer is totally fine.
Okay. I think that I first got into AI or machine learning at the end of undergrad. Most of my undergraduate education was focused in computer science and statistics, but it was very much focused on more of the engineering side. Like we took computer architecture classes, we took assembly classes, et cetera. And at the very end, I took my first AI class. And we had this class competition about trying to play Connect 4. And at the time, Lee Sedol was playing Go against DeepMind. And I was like, this is fascinating. I want to try applying deep reinforcement learning to our class competition. And that made me get really excited about this. But unfortunately, I was at the end of my undergraduate time. So I didn't know what to do. And I ended up doing two different things. One of which was I went to go work in biotech, where I used deep learning to do DNA sequencing. And at the time, this is pre-transformers. There are these things called sequence-to-sequence models, typically LSTM-based. And people were interested in, could we apply them instead of from text? Could we instead apply them to actually take sequences of light and convert that to nucleic bases? So I spent some time at this big biotech company called Thermo Fisher, where I earned my first patent. But I was also very interested in trying to do more AI, and I didn't know what that looked like. And at the time, I'd been attending Stanford's Computational Neuroscience Journal Club, which was really starting to focus a lot more on deep learning. And a lot of the people said, if you're interested in trying to get a job doing this, you really need to have a PhD. And I had been applying to a bunch of industry positions. They said, you really do need to have a PhD in order to be qualified to do research. So I said, okay, that's fine. At the time, it was like late May. And I think the only places that were still accepting were British programs, which actually turned out to work really nicely because the British education system is really, really good in many regards for neuroscience. So I ended up going to London for a year where I worked at University College London on computational cognitive neuroscience. That was super fascinating. Through there, I met some people who were at Uber AI Labs, and they referred me to work at Uber. So I worked at Uber for a year, and then I left to do a second master's, this time in computer science on the East Coast in Cambridge. And then after that, I then came here to start my PhD. So that's kind of the meandering path that ultimately led to where I am today.
Interesting. And when you first started your PhD, or even at Uber, like what were you interested in? How did you get interested in the
Absolutely. Yeah. So I actually came to Stanford to do my PhD in a much smaller field that many people might not be aware of. It's called Neuroscience-Inspired AI, Neuro AI. Mm-hmm. And I came to work with two particular professors here who, they are independent, but they also closely collaborate. They sit on the same floor. They supervise many of the same students. So they're closely intertwined. I came here to work on taking insights from neuroscience and trying to use that to build better machine learning models and algorithms. That was the plan. And the end of the first year of my PhD, I was now in this scientific disagreement with two professors here. And we published a refutation of their work at NeurIPS. And at that point, it was very unclear to me what to be doing.
Mm-hmm. That makes sense. And on the research side, I'm curious, if we were to get into the actual research interests you had at the time? Like, why did you do neuroscience-inspired AI? And what was your evolution of your beliefs around those ideas as you worked on it?
Absolutely. So I had an argument, and in retrospect today, I think that argument was wrong. But the argument at the time was, keep in mind, this goal of pursuing this particular topic, I think I really started back in 2017, 2018. And at the time, models were quite inept. And many people felt that if you really want to build better models, you have to understand basically the sole organism that we know of that seems capable of solving these complex, hard tasks, and that's humans. So the thesis was, if you want to build better machine learning algorithms, you need to reverse engineer whatever the biological brain is doing. And so that was the neuro AI thesis of figuring out how the brain does things, taking those insights, and then making better machine learning. And the reason why I no longer believe that is because, I think it's just empirically false. So, that should be enough to persuade anybody. I think we're now having amazing models, and we didn't need to understand anything about the brain. But I think that even back in that time, even before scale had entered the picture, even before we had these amazing models, I think there was still a very clear argument, maybe two arguments to be had about why that reason was fallacious. One of them is people at the time, a lot of faculty and a lot of prestigious people talked about how understanding the brain is really what's going to be necessary for these breakthroughs. And they talked oftentimes about a lot of the commonalities. So for example, DeepMind was very big on how deep reinforcement learning was inspired by the brain, and how replay, which was fundamental in DQN back in 2014, was inspired by the hippocampus and so forth. But if you look at the history about most of the transactions or exchanges between machine learning and neuroscience, by the way, when I say neuroscience, I mean neuroscience broadly. If you look at the exchange of ideas, it basically was almost always historically from machine learning to neuroscience. There are not many examples, I think, that go in the opposite direction. And I think that when you really dig into the historical record, that becomes very obvious. So the people who were really promising that neuroscience is the approach, I think either didn't understand the historical record, or maybe themselves were just mistaken.
That's really interesting. So basically, we're kind of like, our models of neuroscience are actually we're like understanding the human brain by looking at how machines work, but not the other way around.
Exactly. Yeah. So that was one reason. And the other reason was the task that the biological brain has to solve is very, very different than what an artificial network has to do. And to me, the clearest example of this distinction is whatever solution the brain has learned to produce intelligent behavior has to go through this sort of genetic bottleneck where we cannot pass on fully formed brains, right? So instead what we do is we compress whatever algorithm we have, whatever model we have, into DNA, which is, a couple gigabytes, and then we pass it off to our offspring, and they have to rebuild this. So whatever solution that favors is going to be good for passing through this bottleneck, and that's fine. But there's no reason why artificial intelligence has to pass through a similar bottleneck. So the solutions are going to look very different.
That's super interesting. This is the best argument I've heard for why biology is not necessary to understand to build machine intelligence.
Yeah, and once somebody explained that to me, I was like, that makes a ton of sense.
And so after you spent this time in neuroscience and maybe this fight happened, and what happened? Like, how did that change maybe both your approach to your PhD, but also your research interests?
Yeah, so it changed both how I approach research, and it changed the content of the research that I wanted to do. How to approach research. Let me try and paint a picture about the situation I was in at the end of the first year of my PhD. I had come to work with particular professors. I felt that they had done something that was borderline academically dishonest. I was no longer going to work with them. I had published a very public refutation of their work. And the way that my program works is you need to have funding from your professors. So I had come to this institution. I didn't have any funding. I didn't have any advisors. I also had to take a leave of absence because I wasn't going to work with them. And when you take a leave of absence, they kick you out of housing. And then because I left housing early, I lost my income. And when you're no longer a student, you can't live on campus because you're no longer a student. So I had to leave housing, and then I had to pay an early exit fee. So at this point, I had no advisor, no housing, no income, basically no future at Stanford. And that then meant when I returned, then I returned in the fall, and I was struggling to find a new advisor. And I was struggling for a variety of reasons. People here are extremely busy. The credentials I had previously, they didn't care about. They didn't care about this neuroscience stuff. They're like, sure, you published at Neuro, so is everybody else. Who cares? And some professors turned me down because of the fight with the previous professors. They said, one professor told me, he said, I really respect this work, and I think somebody needs to do it. But one of the professors who you beefed with was my postdoc advisor. I'm pre-tenure, and I cannot risk my career for you.
Oh, man. Yeah, rough.
Okay, so that's fall. Can't get an advisor. So I'm now in a very precarious spot. And I've talked to basically everybody in our department. I start a new rotation with one of our newest faculty. To me, it's very clear that this is basically do or die. It's like, I have to deliver a project that this professor is going to like a lot and convince him that I'm worth keeping. Otherwise, I'm leaving. And so at that point, that was a very strong motivating factor. That was the origin of the emergent abilities, our emergent abilities, a Mirage NeurIPS paper. I started that project with him, and it turns out that he and I work really well together and have continued to work really well together. In terms of the content of the research, I think at the time, one of the really nice things about my advisor, Sammy Koyejo, one of the really nice things about him is he has very broad interests. And I do too. And so it was very easy for us to come up with a large list about topics that interested both of us. And it just so happened that we had overlapping interest on this particular topic, and it was really timely.
How did this emergent abilities paper come about?
Yes.
It was a paper that we found very interesting and actually really affected how we design all of our evaluations for our models.
Interesting. Okay. First of all, that's amazing to hear. I love hearing that people took it and used it in practice. The origin story behind that was I was actually at the time working on a project with him. So this is like week 3 of winter 2023. I was working on a project. And interestingly, this other project we were working on, a different team would do it, not in our lab, a different team would do it. And it went on to be a different NeurIPS oral. But the Emergent Abilities Mirage paper was, I was attending a lecture by one of the authors. And I think the key insight of the paper, which is that how the humans conduct evaluations can affect the results, and that you need to think through how you're evaluating models because that makes a difference, which is, by the way, I don't think a very profound insight. I think it's straightforward. But anyways, I was attending a talk by one of the authors. And one of the things that's very apparent in the first figure of the paper is that all of the metrics that emergent abilities were displayed on are these very harsh metrics. They're very stringent judges. I think in the first figure, I think there's 8 subpanels. And I think 7 of the 8 metrics are accuracy or exact match. And those ones are like, as I'm sure you're both aware, those ones are, you either get full credit or you get nothing. There's no partial credit. So at this point, I raise my hand in the audience and I say, I'm just curious to know, it seems to me like the metrics might be playing a role here. How did you guys investigate and rule out this alternative hypothesis? And I was expecting the author answers and said, there's no way that's possible. And that was the moment, because you're sitting there thinking to yourself, I'm not saying that this is the correct alternative explanation, or that the given explanation of emergent abilities is wrong. But surely we can agree that how you assess models, and if you use really, really harsh metrics, could produce some like if you use a discontinuous metric, you might expect your models to display discontinuous abilities. And the author was adamant that this could not be possible. And then I went back to my computer, and that afternoon I ran some toy simulations that ultimately became, I think, figure 2 in our paper. It shows how you can use different metrics on the same data to get emergent abilities or to get non-emergent abilities. And I sent it to the author. And the author was like, I had no idea that this was possible. So at that point, it was then like, well, if they didn't know about this and if they didn't investigate it, still the jury's out, but we should now run some experiments. So let's start querying GPT-3. At the time, that was the family that had multiple models of multiple scales that was available. And it seemed like the initial predictions, we had 3 initial predictions and all 3 of them were borne out. And that was basically the paper.
And for the audience, can you walk us through what were the 3 initial predictions that bore out?
Yeah, the paper is a story about predictability and surprise. The predictability for the past 5-7 years, we've been seeing these very, very predictable behaviors of large models, where if you put more data, more compute, more parameters into them, they got better in a very predictable manner. And these are called neural scaling laws. But then that story started to change around 2020, where people found that in general, while the test loss was predictable, there were these specific behaviors that seemed unpredictable, that were surprising. So perhaps one of the most famous ones was in this GPT-3 paper, where they found that as you make models bigger and bigger and bigger, the small models are wholly unable to do arithmetic. But then at some seemingly unforeseeable model size, the models are able to do arithmetic perfectly. And it was just this rapid transition from wholly incompetent to complete mastery. So this phenomenon was explored by many other people. There are other papers as well, and it was ultimately termed emergent abilities. And to just briefly summarize the paper that we worked on, our emergent abilities in Mirage, what we asked is whether or not these abrupt, unpredictable changes in the models, we asked, are they really due to fundamental changes in the models, or are they due to how human researchers run their evaluations? And that was really the paper. And I think the punchline, I think the jury is definitely still out. I think there's a lot of really interesting work being followed up about, can you get emergent abilities? And I think that maybe you can. But I also think it was helpful just for the community to think through the interaction, because there was three things at play here and how they interacted. There's the question about like how your models improve predictably. There's a question about how you evaluate them using the metrics. And there's a question about the resolution you have, the amount of data you have in order to run these evaluations. And so the whole point of our paper, to me, the biggest takeaway is, if you want to make predictions about your model's capabilities, you need to think through the interplay between how the model changes predictably, the data you have to do your evaluations, and the metrics that you use to do those evaluations.
Mm-hmm. That makes sense. And one of the most striking things for us from that paper was this idea of how stringent the metric was and how that mattered for whether an ability looked emergent or not. Because of course, if you don't get no partial credit, then of course you can't, then it looks emergent. You can't tell if progress is being made. And so I'm curious, you mentioned like, it feels like the jury is still out on whether emergent abilities are real or not. What are your thoughts on this and your intuitions on this now?
Yes. So first of all, it's very hard to study. At least it's very hard for someone like me to study. And the reason I say that is because in order to understand how models change at scale, you need to be able to run experiments. And I, as a PhD student, just don't have the ability to engage like that. I presume that leading companies like OpenAI, I assume that they have a very, very clear answer. That's kind of me dodging the question. It's saying that I really don't, like, epistemically, I don't have the right knowledge in order to answer this question. But there are some interesting papers that I don't want to stand behind, but I am grateful that people in the community are pursuing and questioning. So one of them is by someone named Eric Michaud at MIT, and he studied this quantization hypothesis of scaling. And what he studies is, you imagine that your data set is comprised of individual bits, little pieces that he calls skills or quanta. And the idea is that a model of a fixed size can only pick up some finite number of these skills, acquiring them from the training data. And so then, in order for me to do a task, I need to have, let's say, skills 1, 2, 3, and 4. A small model might only have capacity to pick up skill 1. A medium model might have capacity to pick up skill 2. And then model 3, skill 1, 2, 3. But still, it's not enough to do the task. But then once you finally get the critical size model, then it can pick up all the skills, and then you do get emergent abilities. Now, that paper, I don't want to mischaracterize the paper. It's been a while since I read it, but my recollection is that was demonstrated on simple MLPs that were performing bit parity tasks. So does that say anything about large models? I'm unclear. There is other work also looking at emergent abilities. There's also a dispute about what exactly emergent abilities means. So there was a follow-up work that recently came out, and I'm trying to remember what, it was really funny. They said that models genuinely do display emergent abilities, but it seemed to fundamentally misunderstand what the term meant. What they did is they said, if you look at the downstream evaluations, you get very unpredictable behavior. But if you look at the pre-training loss, then you get much more predictable behavior. And if you extrapolate the pre-training loss and then try and predict from that what the downstream behavior will be, that extrapolation goes a little bit better. To me, it didn't really justify the claim. The point I was trying to make is there are people who are researching this, and I think the jury is still out.
Maybe one question I have is, based on your paper, actually, we made all of our evaluations continuous.
Okay.
Not like 100% continuous, but like our metrics are fairly continuous. And so we can kind of tell, like, are we improving the metric by changing various parameters, by changing our data, et cetera. And that has been really helpful. We can tell if we're getting better. One thing that we are curious about is this idea of maybe skills is not quite the right idea, but so you mentioned, there's this idea that once you have all the skills, now you get this ability. The ability requires all of these different skills. But skills aren't quite binary. A lot of our evaluations are like very fuzzy in terms of skills. You can kind of guess roughly in a direction that's kind of similar and like gets close without really understanding the task. There's like lots of things that feel very fuzzy about a quote unquote ability.
Yes.
And I'm curious, like, I know you spent some time at Meta studying Llama and working with language models. And I'm wondering, do you have intuitions about language models that maybe are like either after this paper, either about emergent abilities or other intuitions about models?
Yeah. And this is, I think, a very common refrain in the industry today is that people run evaluations. And I was on the Llama evaluation sub-team. And I want to be clear, I don't speak for Meta. I think there's a common refrain both in Meta and across the industry of vibes being the only evals that matter. So, I don't want to tell you something you've already heard, but tons of people are, I don't care whatever quantitative numbers you come out with. It's great that we have them. And maybe for a press release, we want to show that we're better than competitors. But at the end of the day, I care about, is a human going to engage with my model? And the only way to get that experience is to play with the model yourself and ask it questions. And so people call these vibes evals. And to me, it's obviously, it's a really non-quantitative method. And I think a lot of people in the field are evals, by the way, I should just say broadly, evaluation of language models right now seems like it's generically a mess in a variety of different ways. And many people have talked about whether or not there's potential startup opportunities in the sense of like building some sort of auditing industry. And lots of people are doing this. There's all these startups doing evals. Yeah, it's just generically a pretty bad situation. On the particular topic of the vibes-based evals, the question just there is like, it makes sense, but it's non-quantitative. We need to make it somehow more rigorous.
Yeah, so it sounds like vibes-based eval. That's really funny, first of all. But it sounds like vibes-based evals are like, okay, does it feel good as a human to use this model versus model to score well on this benchmark? But in theory, you should be able to capture what feels good and what doesn't feel good. Did you try to do that, or kind of what's your experience with that?
Yeah, so actually one of the projects that I worked on at Meta is about using NLP benchmarks. So, we have 20 plus years of these things. And before we had chat LLMs, we typically evaluated models using them. The project that I worked on was about using these NLP benchmarks, which are fast and cheap to run. Can we use them to predict human evaluations of language models? And obviously, there's not a one-to-one correspondence between a particular prompt that the human asks and a particular sample within MMLU. That's a common benchmark. And so it was really this kind of very aggregated level of analysis. And the answer is actually yes. You can have a really pretty good sense. And it turns out that depending upon what you care about your language models having the ability to do, different NLP benchmarks are better or worse at predicting that.
That totally makes sense. I think internally we care a lot about reasoning, and we don't test on MMLU because it's about, for a large part, memorization of facts.
Yes.
And so, yeah, that does really change things. I'm curious, what did you learn? Like, what's your intuition about what you learned from this project? And what was predictive?
What was predictive? So when I say human evaluations, just like how there's multiple NLP benchmarks, there's tons of human evaluations. And there's different categories. And we have this whole taxonomy, and the paper is under review. The only broad takeaway I can tell you is that basically for almost any human evaluation you care about, there are some subset of the common NLP benchmarks that can be predictive of it. In terms of knowing like what specific for you, you're like, I want to know for a particular set of human evaluations, what is the right subset of NLP benchmarks I want to look at? That's going to be very specific upon the choice of the human evaluation. I could tell you a couple of examples there. One of them was we were looking at the ability of language models to role play. So it turns out a lot of companies really care about this. So for example, like Character AI, right? Their entire business model is about having their models role play as whoever. And you might ask yourself, are there NLP benchmarks that are really good at that? At predicting how well models are going to score in terms of pretending to be historical figures or pretending to be popular celebrities. And it turns out one of the things that we found, one of the most predictive is a subset of MMLU called jurisprudence. And we're like, what the hell is jurisprudence? Isn't that like law? And it turns out if you open up the benchmark and you look at the actual samples, they're all hypothetical role-playing scenarios.
That's so interesting.
It's like, suppose that you're married, your wife is in labor, you're rushing to the hospital, and you run a red light and you crash into a car. Should you receive less of a punishment because you had an urgent medical consideration? And then the language model has to be like, yeah.
That's awesome. That's so interesting.
So that was one surprise. Then there was another surprise, which I'll briefly mention. One of the best metrics we found, or like one of the best general purpose NLP benchmarks, actually comes from the inverse scaling benchmark. Inverse scaling, I don't know if you're familiar with this. This is work that I think the senior author was Ethan Perez. And what they were interested in is, are there tasks? So this is all background about inverse scaling. They were interested in are there tasks where bigger and generally more capable models actually do worse as they get bigger? And I think the general consensus is not really. There are some where, like, if you're in the mesoscale, the models will do worse than if you just keep getting bigger and bigger and bigger, you'll then get better. So you work with Jamie, right? One of his papers is about stepwise behavior of self-supervised learning. And this occurs not just for self-supervised learning, which is great. It also occurs for other things like deep linear networks. And people will frequently observe that their loss curves have these plateaus. And they'll be like, oh my God, what is going on? This is like mind-boggling. And I have no idea. This is super. Just last week, I was chatting with a guy who had these results and he was like completely stunned. And I said, like, we understand that this occurs in deep linear networks. We understand that this occurs in self-supervised learning. Why are like these non-monotonic behaviors? I mean, even that is monotonic. So the inverse scaling situation was people, right? So the background context was, can we find tasks where the bigger models do worse? And the answer was generally not, but they had tasks that are interesting. One of the tasks that we found was really important was this one about overriding the language model's default behavior. So you can imagine that the way the task worked of this inverse scaling task is, it would be like all's well that ends. And the instruction would be, do not finish this with the typical ending. And there was evaluation about maybe specification about what you should do instead. And we found that this was broadly highly predictive of human preferences. And it kind of makes sense in the way that when I'm dealing with the language model, it has its own prior inclinations. But when I'm interacting with it, I want it to do what I want. And so I care about, is it willing to overwrite that prior inclination in order to adapt to what I ask? And so that's inverse scaling. Yeah, I thought that was really cool.
And so you have a paper coming out, presumably, with a lot of these correlations between benchmarks and human evaluations.
Exactly.
What are some other attributes, aside from ability of models to role play and also human preferences, like what correlates with human preferences? Are there other human evaluations in this taxonomy that you were interested in?
We actually had a really big taxonomy, and we just didn't have time to collect all of it. The taxonomy included things like factual questions, writing content creation recommendations, language assistance, and that could be in your own native tongue. It could also be in a foreign tongue, and then also just dialogue. And dialogue can be on a huge number of topics. It can be about things like helping somebody rewrite an essay. It could be about reasoning through a math problem. It could be about coding. It could be about extracting insights from some piece of text. It could be about brainstorming. So there's tons of human evaluations we were considering in this taxonomy.
That's super interesting.
Yeah.
Interesting.
There's a lot of evaluations that you oftentimes want to run, but they're very, very expensive. So for example, like generative evaluations where you're producing code and testing what the pass rate is, these can be very slow and expensive. So another project that we also worked on is, how do you downsize evaluations to just get the same result, but much faster and much cheaper? And in fairness, when I talk about the expense, it's not like pre-training a model. It's several orders of magnitude less costly. But on the other hand, like, I don't want to have to sit around for a day or a week to run all of these evaluations. Can I just cut them in by a factor of 10 or by a factor of 100 and still get the same outcomes? So it turns out the answer to that is yes.
Interesting.
Yes, which is
more about that.
Yeah. So this is another project that I worked on that hopefully is coming out soon. There are two sort of engineering use cases, one of which I'll call model comparison. So you want to train multiple models, you want to look at different data mixtures, architectures, whatever, learning rates, whatever. And you want to compare, is A better than B? And what you'll find is, if you then run your evaluations, because you have all of these samples, they take a long time. And then you're left with these error bars that tell you an unclear story.
Yes.
Okay, and you're kind of squinting at this and you've got a billion of these because you have all these different evaluations and you're like, well, this one's slightly better than that, but then on this metric, that was better. Or then that's one problem. So I'll call that the model comparison problem. Then you have the scaling predictive problem, which is, I'm not comparing A versus B. I just want to pump in $5 million of compute, measure the performance along the way, and then I want to be able to extrapolate. And in that case, you could imagine that if I have massive error bars, then the forecast could be extremely high or extremely low. And it's very hard to do forecasting if you have really, really large error bars. And so the project that we worked on is, how do you get faster, cheaper, and also smaller variance, lower variance predictions for evaluating models? And the way that we approach the problem is, I think, quite intuitive. What we said is that these data sets, everybody takes them as given. And if you want to compare my model with your model on the same fixed benchmark, then that makes perfect sense. And that's what we do. The problem is that those evaluations to have an apples to apples comparison are not the evaluations that we care about when I want to do model comparison or I want to do compute forecasting. So benchmarking, running the evaluations, that's fine. In this particular case, for these two use cases, we want to modify our evaluations. So how should we modify the evaluations? And the answer is, we said, these data sets, we're not going to take them as given. Instead, what we want to do is we want to learn a resampling, a reweighting of the samples in the benchmark with a couple of just two simple desiderata. One of them is the reweighted data should produce the same performance as the full data set. When I say produce the same performance, I mean, like, if I take two models and I run them on 50 NLP benchmarks, and then I compute, say, the average score on each benchmark under a fixed metric, under a fixed prompting strategy, whatever. I just want the original data set, the full data set, and the reweighted data set, I want them to yield all the same values.
Interesting, quite clever. So you're finding basically like what are the
support vectors for
the support
exactly.
vectors
support
for the
vectors.
data set. Yeah.
Exactly. Yes. And then the second desiderata. So it's like I want to preserve the predictions. And the second thing is I want to crush the variance. It turns out that you can downsize a lot of data sets by like 90%, or even as much as like 95, maybe depending on specific data sets, like ARC, for example, you can really get away with a lot. And then you just get much faster, cheaper evals. It's really nice because oftentimes for these generative tasks like MVPP or human eval, oftentimes you can be stuck waiting for models to generate a lot. And if you care about making predictions, you want to make sure that you're generating enough data to have good resolution. So that takes even longer. And so having a way to figure out that some samples are not worth considering, that sounds really good to me.
That's super cool. That's really clever. I love that.
Are there other papers that you were really excited about? Other bits of research where you're like, oh, this is the thing that I definitely want to like broadcasting it out there. Something I learned, something surprising.
Yes. So I would love to talk about something that I've worked on for the past 2.5 weeks. This is a 3-part trilogy. The first part just came out on arXiv today. The second part is probably coming out in 2 days. The third part will take a little bit more time. The first one is about a phenomenon that's called model collapse, which is what happens when large-scale generative models are trained on their own generated outputs. And this is a really interesting question. There's been a long line of research about it over the past maybe year. And we have a paper that says a lot of the previous work was misleading. Our takeaway is that we don't think it's a problem.
Basically, yeah.
The second one is the reason why we did this model collapse adventure for the past 2 weeks is Claude 3 had just come out, and we wanted to evaluate subjectively how good is Claude as a researcher. And so the second paper is talking about our subject. I mean, obviously it's a sample size 1 small scale thing about how well Claude contributed to the first paper as a mathematician, as a scientist, and as a software engineer.
That's interesting for sure.
Exactly.
Super cool.
I'm also curious about the third one.
Yeah.
But
I think the third one is interesting to people who are really care about this topic and maybe less so to others. It's a much deeper theoretical analysis led by some of our collaborators in the statistics department about, in very, very simple but interesting analytically tractable models, when does model collapse occur and why, and when does it not occur and why? And how do you either selectively generate or filter synthetic data to get better performance? Now, this is all small scale stuff. And so, like, if you're a statistician and you love analytically solvable models with Newton laws, then like this is your cup of tea. But I recognize that it's not everybody's.
Okay, this is totally our cup of tea. So let's talk about model collapse and your takeaway around thinking it's not a problem. What led you to this work, and kind of what did you analyze and conclude?
Yeah.
And also the theoretical part, like why does this even happen, is also interesting to get into for sure.
Yes, definitely. So the background, and maybe this is inappropriate, but I feel obliged to be honest. The origin story of this paper was the field was just working on ICML reviews over the past maybe 2 weeks. And I was procrastinating on my ICML reviews. And one of the papers had made a particular assumption that I was like, oh, that's interesting. I wonder how the result would change if we modified the assumption. And at the time, Claude had just come out. It had claimed that Claude had really good mathematical reasoning coding capabilities. And I thought to myself, well, let's see if Claude first can accurately summarize the paper. Can it correctly describe how we want the assumption, this key assumption, to change. And based on this new assumption, can it rederive all the modified results? Can it figure out how the change percolates through the rest of the science? And within, I think, 90 minutes, I had a fully completed, polished 8 or 9 page research paper. I was blown away. I was very excited, but it was late. So I said, okay, I'm going to go to bed. I'll wake up in the morning. I'll check all the maths. And I wake up in the morning and the whole paper is wrong.
Interesting. And so the whole paper is wrong because the math is wrong. The whole paper is wrong.
The math is wrong. Yeah. Yeah. So the very first attempt was just the first paper, the motivating paper, was about studying model collapse in a very simple setting that's analytically tractable. And the reason why that's interesting is because people are worried about model collapse. Perhaps we should describe what model collapse is, but people are interested in model collapse. And this previous paper was a paper that studied sequences of linear models, where I have an initial data set, I fit a linear model, I use that linear model to generate new labels or targets, and then I fit the next linear model to these new targets, and then I then again, generate, fit, etc. And they showed in linear regression that model collapse occurs. And the reason why this is interesting is because we care about our deep generative models, of course, but if model collapse is something that is so fundamental that it occurs even in the simplest setting of linear regression, that seems like a death blow. It's like, this is a fundamental problem intrinsic to all types of deep generative models. So that was the worry. That was the concern. And what we wanted to test, and the assumption we wanted to change, is it turns out that a ton of these papers, so just to be clear, when people talk about model collapse, there's been a series of papers and they have really catchy titles. There's like The Curse of Recursion, Self-Consuming Generative Models Go Mad, all of these titles. And what we noticed when we looked closely at the methods is that we thought that the generative models would be trained on accumulating data. So what I mean by that is you have your first initial real data set. You then train the first model. You use the first model, maybe that's your GPT-4. You use that to generate some additional data. It goes back into the pool. Then you use all the pool to train the next GPT, and then you recurse. So you're imagining that data is accumulating over time. And what we instead found is that all of these papers, if you look closely at their methods, instead assume that data is replaced at each iteration.
Interesting. Okay.
And we're like, there's a practicality consideration for why they do this. It's easier if your data set size is fixed. But we said, what happens if we take the replacing the data assumption and instead ask what happens if data accumulate with model fitting iterations?
So you retrain on the entire pool.
Exactly. That's right. Yeah.
You train from scratch on the entire pool, basically.
That's right. Train from scratch on the entire pool, as opposed to training from scratch purely on the previous model's generated outputs.
Yeah, that makes sense. Like, I guess my model of model collapse, mental model of model collapse is model collapse is a result of lack of diversity. You get this distribution mode collapse. For the audience, this idea of model collapse is if you train a model, you use it to generate data, you use that data to train a model, you use that to generate data. Eventually you just get an output that's not what, it's like outputting just one thing, something like that.
So what you're describing, I would say, is a subtype of model collapse. I might call that mode collapse, where the model collapses to a single or a small number of
collapse.
But there are other ones. So I think a really good one that shows this is this paper by Ala Mohammed, which I think was a iClear 2024 paper. And what they show is sequences of models where you have diverse human high-resolution faces being generated. And over time, for whatever reason, these weird, almost I don't know what to call it, this distortion, almost kind of like whiskers or scars, starts appearing on the human's faces. And then all the human faces start having them. And so you still get a huge amount of diversity. You get diverse backgrounds and faces and ethnicities, but they're all now warped in this consistent way.
I see. So what's happening is when you're training, so this assumption that you're training only on the generated data set, kind of what happens is if your generated data set has some weird feature in it and you're only training on the generated data set, then of course you only get data set with this, you get model with this weird feature. And so you suddenly just develop whiskers, you keep the whiskers.
Particular whiskers are probably an artifact of the way that the actual model is encoded, the particular image generation thing that's happening has these sine wave features that just happen to work out to have features in this particular place, overlap in this particular way, such that it's very subtle and they're there in the original ones, but it just becomes more and more pronounced over time.
Right, that makes sense. So exactly. Then you would expect okay, I see. So you kind of kept the original data set and then you accumulate. And so then what happened?
So we said, let's just start with linear regression. linear regression, what a previous paper showed is that if you do this iterative fitting of linear models with added noise, the error will increase linearly with each model fitting iteration. So as you have more and more models, you do worse and worse and worse, and there's no way to avoid it. So we said, what happens if instead you do this accumulating data where you have a big pool, you train models, you add back to the pool of data grows. And it turns out in that case, your test error will get worse over time, but it is upper bounded. It's capped at how bad it can get. And that upper bound is actually relatively small. It's pi squared over 6.
Interesting.
And the reason why is because the intuition that I can offer is as you get more and more data. So if we consider a particular model fitting iteration, the amount of data that the newest model adds is proportional to 1 over the current iteration. So if I'm like the 10th model, I'm adding 1/10 of the data because I had the initial data set, I had the first model's generations, the second model's generation. So I'm contributing 1 over 10. And in linear regression, because you have a squared error, that 1 over the iteration index becomes 1 over the iteration index squared. The intuition that I can offer is each model is contributing data indeed, but it's becoming less and less of the total population just because I have so much data. So the errors end up getting, they do contribute something and your test error does get a little bit worse, but it quickly plateaus.
So if you're accumulating data, then I guess it asymptotes.
Exactly right.
Yeah, interesting.
I mean, the other thing that we're ignoring here is like, if you're really generating data, should you just generate data and lump it in there? Absolutely not. Like, you're mostly going to want to apply filters. And now this is also going to cause something like you can get dramatically better by applying the right filters.
Exactly. Right? So for example, like we can do things like look at how similar the generated data is to the previous generation of data and filter only for extremely unsimilar data, or add some like downweight the similar data or something like that, or filter out the things with weird spurious features.
Exactly. And so I completely agree. We didn't in this paper touch on filtering. Filtering, I think, is a very good solution, but we just wanted to see, we had the linear regression mathematical result. We had theorems. The question was, would the same finding hold in large-scale deep generative models trained from scratch, sequences of deep generative models trained from scratch on real data? And so we did sequences of causal transformers on text. We did diffusion models on molecular conformation. And we did variational autoencoders on images of human faces. And in all 3 cases, we actually found, so the results are actually kind of surprising. For language models, we found that accumulating data yields lower error. But for the other 2, for the molecular generation and for the variational autoencoders on images, we found that accumulating, you basically do the same. You don't do better or worse. And we don't know why. But the difference, yeah, please.
Just to throw out a random guess on that one, like language models exist in a much more, I don't have an intuition for the diffusion one. I don't know that much about that domain at all. But compared to the images, the language one is like much more discrete. And so it's kind of useful to fill in the gaps, like extra stuff that happened, but you didn't see in the data set. Whereas for images, like you have all this data, you sort of know all the and you have like a very fine-grained model of this whole thing anyway. So generating an extra thing isn't really it's interesting. There's a huge discrete space of possibilities with language that it's like useful to explore because the language model is sort of under exploring that.
You're kind of saying like language is a latent space already, and
there's lots of ways to say a thing and they all mean the same thing, and that's okay, but you only get to see one of them. And so it's like nice to see a lot of extra variety. I don't know. That's like an informal way of saying it.
I see. That's actually, I'm jotting this down because I think that's really interesting.
I think our pragmatic experience with language models is that this is what happens. And it's like interesting and weird.
I'm curious to know, doubling back to the topic about filtering, maybe you guys already have a solution. But to me, I started wondering whether or not there is a persuasive, rigorous empirical study about if you do have synthetic data, what synthetic data either should you generate or should you select for training the next model?
I don't know one. If you know existing research there, great. We'll definitely be running experiments like that over the next while. I don't know if we'll publish them though. So
yeah, I think we have some intuitions that are not very rigorous. They're just like pragmatically driven, which is like for training the next model, we have like a particular set of tasks in mind, and the model performs well on some subset of those tasks for whatever reason. And so we want to generate synthetic data in the form of like tasks that the model is not quite performing well on, and then that should help its improvement on those tasks.
But then there's a trade-off because as you generate data for the ones the model is not performing that well on, well, it's not performing that well, so it's not right. So then how do you how do you
then you have to like self-select
accidentally got it right? But there's a sort of border where like you sometimes get it right. So
exactly.
It's kind of about a rate at which you can produce things that are roughly correct and like differentiate them with the sort of filtering and
Right. I think Josh's point about the border is good. And then also we work in a domain of code. And so it's much easier to deal with a lot of these things because like you can run it, but there are also still a lot of issues, like some things are not evaluable.
Yeah, I mean, the code evaluations can be run so quickly and can tell you if this is correct or not. Whereas like for images or for dialogue exchanges, like that feedback is a lot harder.
Yeah. Yeah, the boundary of like this data is generated and it is somewhat correct to like correct. Like it feels like finding filters that are able to find that boundary is helpful, would be helpful.
And I guess another thing is like to the extent that you can't find those boundaries, like is your thing really learning something interesting about the world? Like if you want to have a general purpose language model, should it not be able to tell you like this is bad, this is good? Like these capabilities are sort of like they should happen in lockstep. It should not be the case that you can get really amazing at generating and then be like, geez, I have no idea if that's good or not. Like,
although I think
it's been better being similar.
Although it's not necessarily true. It depends on what the model is fine-tuned or RL'd for. So for example, like in general, we have a hypothesis that like evaluation is easier than generation, but there are some situations where this is not true. Yeah.
But anyway, I don't want to go too far on that tangent. I think we were telling us about
that's
some
true.
of these things.
But yeah, it's just the idea that like Claude is highly suggestible and highly will take its own suggestion or your suggestion and just go with it. That causes it be worse at problem solving. That's actually that's very interesting.
Yeah. What really exacerbates this is that Claude, just because it's like, as Josh, I think mentioned, it's been trained to generate things that people are really happy with. And so not only is it generating the wrong thing, but the wrong thing it's generating is very plausible. It looks good. It is, and then you have to then spend a tremendous amount of time figuring out, oh my goodness, it made this really fundamental. Yeah. So it's the combination.
Yeah, it's kind of what you were saying. We go back to earlier about, I think, sort of the second paper or the second thing is this sort of exploration of like using Claude as a software engineer and researcher and mathematician, et cetera. Were there any other learnings from that? Also, I was curious, like, I'm pretty sure I saw some like tweet that was someone being like, wow, like Claude is amazing. It just wrote this new paper for me. Was that you before you went to sleep and then you woke up and it was all wrong? Or was this?
I think that was me before I went to sleep.
Amazing.
Okay. Exactly. In the Claude paper, the way that we write the paper is to deceive the reader. We walk through and we like reach the fake paper and we just leave it for the reader. And they think like, oh my God, this is brilliant. And then only underneath, we're like, actually, everything you just read is totally wrong.
Oh my God. That's amazing.
Reel them in and then, get them. Oh, yes. Okay. To be clear, I'm not punching at Claude uniquely, and I think it is generally really good. I mean, to give a couple of other takeaways from the paper, Claude, one of the things that we found that it's really bad at is we felt that it is terrible at, and by the way, just to be clear, when I say Claude, it's not like we compare it against other language models. So I'm not trying to say Claude is uniquely bad, and I don't mean that in any way. All that I'm trying to say is the model is really bad at coming up with research ideas. It will put out outputs, and they're not good. The things that it is good at, it understands research papers on at least reasonably mainstream topics. It can modify mathematical assumptions. It can introduce notation appropriate. So if you and I were to sit here and say, we want to change this paper and we need some way of mathematically expressing that, the model is great at it. As long as you go step by step and verify, it's good. Now, of course, it'll make errors, but you can just prompt it and point out those errors. Same thing with code. Like its code oftentimes has mistakes. If you're like, does this have mistakes? It probably won't find them. But if you point out, you're like, this line is wrong, explain to me why it's wrong, it will immediately, like, I think that was one of the ones that blew me away, is at one point, I was like, this code isn't working. It was like, I don't know what's going on. And I'm like, look at this line. Can you explain to me why it's wrong? And it said, you're absolutely right. I'm quoting here. The code for generating this variable is incorrect. Let me explain why and correct the code. The issue is that in the non-accumulated data setting, we need to be generating data in this particular way, and we're not using the right way of generating the data. So I have to modify it like such.
Have you tried the opposite of saying this line is wrong and pointing to a correct line?
I've not. That would be interesting.
It'll also give you very good things about like, just wrong, X, Y, Z. And you're like, no.
Yeah.
All sorts of reasons that like, no. It's the same thing happened to me. I was like, wow, it's so good at this. And then I was like, okay, let me run on all the lines. And I was like, it finds errors on all the lines. It's so wrong though. That's so annoying.
One of the things that I wish both GPT, Claude, and other UIs would provide is a tree structure. Because this is something that we use all the time in conversation, and we've used in this conversation that I think is super useful for us to be talking about a topic, and then we go down some branch, and then we pop back up, and then we go down a different branch, and then we pop back up 2 levels. Mm-hmm. And the best you can do is ChatGPT regenerating the latest. Mm-hmm. It doesn't facilitate having this ability to, you can try and do it in a linear manner, but you run into slow generation, long context, and also if there are errors along the way, they accumulate. Mm-hmm. So, yeah.
Yeah.
That's a really interesting thing from like a UI perspective.
Yeah. One of my lab mates is working on, he has structured all of his research in this tree structure, and he's using models to automate his research as like small research assistants. And so he has them like expand the tree of his research and like come back with little results and then tell him what they've built.
That's super interesting. Does it work?
No. But he's trying to get it to work. But I think there's 2 other points that I want to make. One of which is, it feels to me like at least Claude was really good at generating things, and just occasionally it got things wrong and needed to be corrected. And so to me, I'm thinking that if you could have a model that was really good at being a critic, at finding those errors, you just have these 2 talk to each other and you have a fully automated researcher.
Mm-hmm. Yeah, and I think that's correct. And I think that's actually not that far away from what could be done. And in the next year or 2, we're going to see this. And like, people really underestimate how powerful that will be.
Yeah. Oh, interesting. So your timeline is, you're thinking roughly a year until this.
I think that since we're saying like sometimes evaluation is often easier than generation, like if you really focused on that, I mean, these generative abilities are amazing. It doesn't feel fundamentally as a person like this. The critic part is the really hard, is like so much harder. Could turn out that it's much harder, right? But I think we'll see in the next year or 2. But maybe I'm wrong about that. But I don't think that it is.
Yeah, I have a hot take.
Dramatically harder.
Yeah,
I have a hot take. Hot take is basically like the reason why these models are good at generation, so good at generation, but not as good at evaluation today, is because for the user experience of chat, this like chat experience, appeasement. It's hard to get the same model to be really appeasing and also really critical. And in a chat UI, the tendency is to optimize for appeasing the user as opposed to being really critical. And so the use case for the model actually matters a lot. And I think chat as a use case has pulled our models, RLAIF'd or HF'd them into this really weird space where they're super appeasing and good at generating, but really bad at critiquing. And like, there's not much like immediate revenue potential in critiquing because your users will be unhappy. But you know, it is really useful for particular things.
No one wants to sign up for a, $10, $20 and is right about it.
And is right, yeah. But
your whole line is messed up. You should really not do this. That was a mistake. Like, what are you doing over here?
Right. But internally for us, this is something that matters a lot. So we'll have a model like this. Yeah. And I think it'll be an important component for really good larger systems. Yeah.
I'm wondering if the Claude evaluation, we tried to evaluate it in 3 different regards: mathematically, scientifically, and then as a software engineer. And one of the things that I think I was generally in agreement that I think evaluation should be easier than generation. But after thinking about it, it feels to me like the answer feels flipped in math versus coding. And I don't know whether or not you two would agree. To explain what I mean is that oftentimes math proofs are step by step. And I just have to ask, is the step from line 1 to line 2, is that valid? Is the step from 2 to 3 valid? If so, from the premise to the conclusion is valid. Whereas with code, in order to identify an error, oftentimes you need, for example, to simulate the entire process in your head. And so I'm wondering if, to me, it feels like evaluation for math is consequently easier. In other words, it's kind of like watching code be executed.
That's interesting.
I see it executing step by step. Whereas with
I see a similar thing for code.
It feels like code is similar. You kind of follow the next step and then the next step and then the next step. And I see what you're saying about needing a hold state in your head.
Exactly.
I think it's similar for code, but it's not linear. With the math proof, you do all the things in a line, and so they all have to follow from each other. But with code, it's well, if this piece does what it's supposed to, and that piece does what it's supposed to, and that one does what it's supposed to, then I can put them together in this way, and all of these things hold together. But it's there's more disconnected pieces.
I think it's also about holding state in the sense that in math proofs, good proofs explicitly illustrate state, and they put the state on the page. Whereas in code, the state is implicit in the variables or implicit in whatever. Something that we've been thinking about internally is like where to put state, and like manipulating state that is hidden is one of the hardest things for humans to do, and also not fun for
And
models.
it's a thing that you can make the models really good at. Like a lot of things with code, like you write this code, you have some assumptions about, you say email address : string. You know it's supposed to be an email address, but you can make that explicit.
Right.
And when you do make it explicit, you can make it more robust. And so you can spell these things out.
Yeah, you can print out all variables.
Write code because we're too lazy. So
right, you can print out all variables at every line, etc.
You can have runtime constraints where you're like, I never expect this list to be bigger than X. You could check at every step of the program execution. That's kind of slow, but like if you had important constraints, you could always be checking them at runtime, but like you don't want to write them all down. So there are other ways that we could think about writing code that would, I think, really, really help make it easier for language models.
Definitely. The Claude conversation has got me thinking about, and Josh, the projection that perhaps within 1 year or roughly about these models really contributing perhaps independently on their own, what are the norms that we need to be establishing? Like if we have AI involved potentially to a high degree of autonomy in accelerating research, what are the norms
that is something that we think about as a company is like, how do we want to think about like the regulatory and policy and like safety best practices and these sorts of things related to agents?
Yeah,
and
I also think we think a lot about how do we empower people to be good at doing oversight over like these systems. Like agents should generally not be autonomous. Actually, an autonomous agent is a really terrible user experience. I actually don't want to like think of a thing ahead of time and delegate it to something, and then for that thing to go off on its own and access my email and do something I don't know about that potentially returns the result I wanted sometimes, but sometimes it doesn't. I think
there's a lot more thought that needs to go in. Like, I think what I was trying to say is this will work kind of like potentially technically in the sense that you might be able to identify those products and then make much better generations. How do you turn that into something that's like a useful product experience? I think there's a lot of interesting questions there. There's different things that we're thinking about.
Hopefully we'll have something like that soonish.
The scenario you paint is just hilarious. To me, it sounds like less having someone you can delegate to and just like coming in to find out what your 3-year-old has destroyed. You're like, what happened? Yeah.
That's totally true. And like these systems are stochastic by design. And so like, it's kind of like not what you wanted.
Yeah.
Delegate something to a thing. So
yeah.
Going back to research, were there any other things that you wanted to highlight from this paper on the Claude thing or from the model collapse thing that we didn't get to touch on?
I think we touched on a lot of them. Yeah.
So my takeaway from this is that you're probably relatively bullish on model not collapsing.
Yes. Yeah. Agreed.
Interesting.
Do you have a sense for why? And I think that this feels sort of similar to the, emergent capabilities, like this model collapsing. Like, do you have a sense for why this happened in the first place in like a research sense? Like, how did we end up here? Like, it seems like, there's kind of basic things you can do in both cases to be like, look, if you look at perplexity, it goes down, it's nice and smooth. And if you look at perplexity, multiple answers, it goes down and it's nice and smooth. Like, why did it take until 2023 for someone to point this out? It seems a little weird.
Yeah, I completely agree. Over time, I think that there are three of my projects have been, in some sense, having this critical flavor. And one of them is the Mirage paper. One of them is this model collapse paper. The other one is the neuroscience one or the neuro AI one. In each case, I think there were different reasons at play. It's hard to say because I don't really know the people. I can say that with the Mirage stuff, initially I thought, surely people would have noticed this by now. And to be fair, many people did. I think that like 30% of the people who reacted to the paper are like, isn't this obvious? Doesn't everybody know this? Like, who cares? And I don't blame them. I'm totally on the same page.
I'm really curious. Aside from what we've talked about, a lot of what you do is kind of look at something, feel like it doesn't make sense, inspect it, and come up with a new lens. Are there any areas that you're interested in doing this next? Like, do you have any felt sense about like, something feels off here or something feels off here, or any like unusual or controversial thoughts that you might have, intuitions you might have?
Nothing currently. I think that model collapse was the newest one that was at the top of my head, as we've discussed. But what I would like to say is in academia and in research in general, and also to some extent in industry, there is, I think, a strong cultural pushback against doing critical work. To be clear, when I say critical work, I don't mean like thinking critically. That's obviously good and that's always valuable. Like, for example, Jonathan Frankel, who I think is the founder of Mosaic and was recently acquired by Databricks, recently tweeted out that so many ideas they've tried in the field have not worked. And that unless they can implement something, they don't believe it. And that's totally reasonable. That's so valuable. But the problem is none of those insights are shared with the community. So your company, maybe some other company is probably going to have to run the exact same experiments. They're going to have to implement something. It doesn't work out. They think it's the fault of the programmer. You have to investigate and debug. And it turns out that the original idea was just nonsense. Okay, nonsense is a strong term, but I just mean, maybe it could be nonsense, but it could also be maybe there's some key ingredient. Maybe it's more complicated. And so I feel like more people should do critical work and should feel comfortable doing critical work.
That's a contrarian take.
I think that's a good contrarian take. Yeah, we also have the same experience. A lot of ideas are much more complicated than we expected, didn't quite work, don't work as expected. Yeah.
Can I briefly mention 2 examples about why I think people should do critical work and why it's undervalued? Are you 2 familiar with the Michelson-Morley experiment? So this is, I think, possibly in physics, one of the most important experiments of all time. Back in late 1800s, people believed in this luminarious ether, right? About how light somehow propagated through the universe. And nowadays, we no longer believe in this. We instead had, at the time, Einstein's special relativity, now general relativity. And the question is how did we transition from this incredibly dominant idea that now nobody today has heard of to a completely different idea that's now accepted as one of the most profound ideas by one of the most many people consider to be an extremely deep thinker? And the answer that caused this switch is the Michelson-Morley experiment, where these 2 scientists said, what are the predictions that this ether wind makes? And we're going to test them and show that all of the predictions are wrong. And Albert Einstein has this beautiful quote, I'm reading off the Wikipedia page, that quote, if the Michelson-Morley experiment had not brought us into serious embarrassment, no one would have regarded his relativity theory as a halfway redemption.
Wow.
So to me, it's the way that we made progress was by pointing out the current existing ideas were insufficient or inadequate or wrong.
Yeah, that's super interesting. I think there's a general trend of tearing down what exists makes room for new growth. And that feels totally true here. Super interesting. You're the 100%. Eval, the models that are good at eval that are missing. Our research community is similarly good at generation and not as good at evaluation.
Maybe generation isn't here.
Or there's disincentive in a social context toward evaluation.
Yeah,
exactly.
That's actually a really interesting final point to end on, which is kind of incentives matter in the final user, and in academia and in language models, the final users are the people, and people don't like to be wrong. And
or
so or to be told they're wrong. And so these both incentivize a lack of critique, and that kind of holds back the field.
Yeah,
awesome.
Agreed.
Well, thank you so much. This is really awesome. I think this is actually a really good point to end on. We really appreciate having you, Rylan. This is super interesting and love your controversial.
Thanks for listening. If you like this, please consider giving us a rating and leaving a review on Apple Podcast. On Twitter, I'm @Kanjun, Kanjun. Until next time.